So up to now, we've got a pretty nice sort of energy model of how we deal things. How we look at things. We've considered kinetic energy, the energy associated with an object's motion. We've looked at different types of potential energies, such as gravitational or elastic potential energy, energy that's stored in the sort of interactions of the system we're considering. We've looked at thermal energy and how friction or dissipative forces will convert these macroscopic mechanical energies into an increase in thermal energy in our system. And we've also put that together with if there are any external forces acting on our system that displace it, they can do work and increase or decrease the total energy within that system. And we've sort of been using this for a while, settled some examples, seen some examples, and sort of hopefully are getting comfortable with how to use this to analyze different situations. Um, I'm going to pose a question though, which kind of shows what's been lacking in some of our models, and that question is this: consider this wheel here, and if I spin it, if that bicycle wheel is spinning like that, what's the energy in that system, right? If you think about how we've been discussing these types of energy before, well, potential energy, well, it's not going to change height, so there's no change in potential energy. There's no external forces, so there's no work being done. There's no dissipative forces in this idealized case. So we can sit here and think about all those energies being zero. And kinetic energy, what's the kinetic energy of this spinning wheel, right? Technically, the way we've been thinking about it, that wheel isn't changing its location. So if we were to use this 1/2 mv squared, well, if v is the change in position with respect to time, that wheel's not changing its position. That would argue that this is zero. But I think any of us looking at this would say, well, clearly there's things moving. There has to be some kinetic energy associated with that. And in fact, there is. This is just sort of highlighting a weakness or a shortcoming of the model we're using. If you recall, this whole semester until now, we've been using what's called the particle model, where we would represent that wheel just as a dot. We ignore the internal structure of the wheel and think of it as a dot. And in that case, that wheel isn't moving, but it clearly misses some of what's going on here. There is energy when this wheel spins. If we look at it spinning, the rims moving around fast, there is motion in there. There has to be some kinetic energy that isn't captured in this particle model. So today, what we're going to do is slowly build up beyond our particle model into what's called the rigid body model. So what the rigid body model is sort of one sort of step up in our above the particle model that adds that sort of complication. So rigid body, what the name comes from is we actually do consider the shape of an object. It has some spatial extent, some body or shape to it, but we refer to it as being rigid because we make the assumption that that body does not change shape. So it doesn't shear, it doesn't bend, it doesn't twist, it doesn't do anything at it. It maintains the exact same shape, but that shape can move, it can rotate around different axes. And using that model, we're able to actually capture that type of energy that was missing, that we weren't accounting for when we used the particle model. And we're going to come back to this rigid body model later on in the course as well. But for now, we're just going to consider it in terms of energy. Um, when we do this, what it adds to this is, so in the particle model, we had this sort of translational kinetic energy. If the object changed position, we could easily assign a kinetic energy associated with the speed of that object. Now that we have the rigid body model, we can also consider the rotational motion of that rigid body, how it spins, and putting those two together will capture the sort of full type of motion of that object, and we'll consider both a translational kinetic energy and a rotational kinetic energy. So how do we do that? Well, first, let's consider some just arbitrary shape. All right, we have some object like that, and let's give it an axis, an axis that it's going to spin around, and we'll say it's spinning with some angular velocity omega, right? Now again, it's not changing its position. For now, we'll just assume it's pinned on some hinge or something and it's spinning around that axis. Well, how would we consider the kinetic energy of that object? Well, that object as a whole isn't changing position, but what we can do is we can break this object up into a bunch of tiny particles, right? It's made up of different things. So if we were to take, say, this little chunk of the object, we'll call this mass 1, right? At some distance r from the axis, we'll call that r1, it's moving with some velocity v1, right? So I know the kinetic energy of that first particle is 1/2 m1 v1 squared, right? That's just our particle model applied to just that, that little chunk of mass. I can then do that to another object, another chunk of mass here. We'll call that M2. It's at some radius R2. It's going to have some velocity V2. And its kinetic energy is equal to 1/2 M2 V2 squared, right? And I can keep going, right? We could have, over here we have mass 3 at some R3 moving with some V3. Right? And its kinetic energy. And you can hopefully see the pattern we're going here. And I can do this for this whole massive object and go through it all and figure out all of these things and come up with the kinetic energy, the total kinetic energy of this whole object would just be K1 plus K2 plus K3 plus dot dot dot, or the sum of all of those kinetic energies, right? And we can do that, and that's essentially all we have to do with this. But we can get a bit more clever with this, because no one wants to sit here and calculate in million or Avogadro's number of kinetic energies. So we can start to look at this and say, okay, well, what is V1? Well, we know V1 is this is moving in a circular path of radius R1, and we know from our kinematic, our rotational description of motion that tangential speed, the V1 it's moving at, is R1 times omega if it's spinning in a circle with that angular velocity. Just like V2 is equal to R2 times omega. It's moving at the same omega, just at a different radius around that. Likewise, V3 is equal to R3 times omega. So we can plug those in to our total kinetic energy, which is the sum over 1/2 mi vi squared, and we get that kinetic energy is 1/2 mi ri omega squared. But since omega is the same, this is a rigid body, every part of that body is rotating with the same angular velocity. This can all be simplified. We can factor out that omega squared, and we get the sum over I mi ri squared all times omega squared. And this gives us the kinetic energy of that object. And it's what we call the rotational kinetic energy, because all we've considered is the energy associated with its rotation. And this is how we calculate rotational kinetic energy. This quantity in the brackets is the only thing that sort of depends on the object. It depends on, where the mass is and how far it's distributed from the axis of rotation. And we call this, we give it the symbol I, and that is what we call the moment of inertia. And it's defined as the sum I over mi ri squared, where we're summing over all the infinitesimally small masses that make up that object. And we can also, as we've just sort of derived, what we can associate, the kinetic energy associated with that rotation is then just 1/2 I omega squared. And relating back to the translational kinetic energy that we had from our particle model, that's still 1/2 mass times velocity squared, where that's the total mass squared. If we put those two together, we get the total kinetic energy associated with a rigid body that can be spinning and having a rotational kinetic energy, or changing its position and having a translational kinetic energy. And again, The rotational kinetic energy is going to depend not only on how fast the object's spinning, but on that moment of inertia, which depends on how that mass is distributed about the axis that it's rotating on. So essentially, if you have an object, say this cylinder here, where a lot of the mass is centered around right near the axis, well, that's a lot of mass that isn't going to be moving very fast because it's near the middle, and that speed depends on how far the size of the R. Whereas if you had something that had a very heavy rim out here, most of the mass is traveling along this big circle. So for a given angular velocity, it's going to have a higher kinetic energy, and that's all captured in the moment of inertia, which is sort of a how the mass is distributed relative to the axis of rotation. Smaller moment of inertia, easier to spin up. You're not moving as much mass. Larger moment of inertia, harder to get spinning up. More mass is moving a larger distance, so it's going to have a more kinetic energy. To actually calculate quantitatively what those are, remember our definition for moment of inertia was the sum over MIRI squared, right? If you have a continuous object like this where the mass, is everywhere in different chunks, you're not going to be able to sum all those particles together that's obscene. But thankfully, we have calculus, and this becomes an integral over the whole volume time with a density and a dm. But the act of doing this integral is sort of beyond the scope of this course. It's a three-dimensional integral. It's really complicated, but thankfully there are common shapes of objects that we have, and the integrals are going to be the same for that shape if it's uniform mass or uniform density, no matter what size it is, right? So if you have, and you can just look up those moments of inertia in tables where the integrals have already been done. So if you have some long rectangular rod that's being rotated about its center, well, if it has a total mass of m and a length L, we know that its moment of inertia is that. The integrals have been done. If it's spinning about the end, so its axis of rotation is around its end, it's going to have a slightly larger moment of inertia, which makes sense again. If this is spinning around its center, the the masses are going around a circle like that. They're not moving as much, so there's not as much kinetic energy. Whereas if it's spinning around this end, these masses are going much farther. So if they're spinning at the same speed, more kinetic energy, it's going to have a larger moment of inertia. Likewise for planes, cylinders, rings, spheres, hollow spheres. You can just typically look up what those moments of inertia are for these large solid objects. So really quickly, let's run through an example from the textbook of how we can sort of use kinetic or rotational kinetic energy in a rigid body model to solve problems that would have been difficult previously. Start off with this one. We have a 1 meter long rod hinged at one end, connected to a wall, released, held out horizontally and released. What's the speed of the tip when it hits the wall? Well, that's my wall. Here's my little hinge. I have my rod that's 1 meter long, hanging out of the end. I release it. It's going to swing down and strike the bottom here. What is the velocity of that tip, right? And this is 1 meter long, right? So we've looked at similar type problems where we just have an object that's changing its height, and we have that gravitational potential energy. It speeds up, it converts to kinetic energy. Looking at this, we're going to assume the hinge is really good, so we're going to ignore friction. There's no significant friction, so we don't have to worry about increases in thermal energy. There's no external forces doing work on the system, so we know that our mechanical energy is conserved, right? So this is how we would probably want to approach this problem, which means our initial kinetic energy plus our initial gravitational energy is going to be equal to our final kinetic energy plus our final gravitational energy. Whoops, final potential energy. And now it's a matter of just, well, let's figure this out, right? So initially, this is released from rest. I just held it out here and I let it go. So that kinetic energy is zero, right? My gravitational potential energy is just going to be the mass of that object, mg, times the height. And if we, call this the lowest point it's going to get when it flips to the bottom 0, this height is just L, right? So it's going to be mgl is the gravitational potential energy when the rod is at the start, when it's not released. What about at the end? Well, at the end, now it does have some kinetic energy. It is rotating about this axis, right? But that axis isn't changing its position or anything. So this is just going to be k rotational. It's going to be that rotational kinetic energy, which we just sort of derived. It's 1/2 I omega squared. What about gravitational potential energy? Well, this is a little subtlety. It's kind of tricky with our rigid body model. What do we use for the height, right? At the end, this rod's going to be sitting like this, and it's going to have, that's its position. That's what it looks like. What is the height? Well, you could argue, well, this end's at a height of 0. It's at our 0 point. But then again, this end is at a height of L still. What do we use for the position of our gravitational potential energy? Well, the answer is you can kind of think of it as, well, I average sort of all the positions of all the masses that make that up. And what you end up is with what's called the center of mass. And now we'll get into more detail on the center of mass later in the course. For now, when we're dealing with uniform objects like this, where it's a uniform density, the center of mass is the geometric center of that object. So it's just at this L/2 height, right? And if you can think about it as, averaging the gravitational potential energies, the positions of all those little particles. So you have an L and a 0, those would average to L/2. Then you have slightly less L, but slightly larger at the bottom. You're going to get that L/2. So this ends up being mg L/2. Now we have we've basically just plugged in what we know about the different types of energy. We can start to solve. The only thing we don't really know here is that omega. So bringing over this term to the other side gives us mg L minus L/2, just gives me L/2. And that's going to be equal to 1/2 I omega squared. Now we know that this rod is just a long rod and it's spinning about its axis. So we know that our moment of inertia, well, we can just look it up from the previous table. A rod spinning about the end of its end has a moment of inertia of 1/3 times the mass of that object times the length of that squared. So when we come back here, we know the moment of inertia is 1/3 ml squared, right? So we can plug that in and we get mg L/2 is equal to 1/2 1/3 ml squared times omega squared. We can do a bit more algebra. The 1/2s cancel, the m's cancel. This L cancels with this one of those L's squared. So we end up with 3g divided by L is equal to omega. I'll take the square root of both sides. We end up with the angular velocity when this rod ends up hitting the wall here is equal to 3g divided by L. The last thing we have to do is actually take that angular velocity and convert it and use it to determine what the speed of the tip is, right? That tip is moving in this circle of radius L at some angular, at that angular velocity. So this is going to be L times omega. This is just that tangential speed is r omega, but the r is the length of that rod, how fast that tip's moving. So this ends up being L times square root 3g over L, or 3g L all square rooted, right? And if we plug in the numbers, 9.8 meters per second squared, L is 1 meter, and that this ends up being 5.4 meters per second is the speed of that tip, right? And we've solved that problem. Again, when we're looking at this energy stuff, it's the same thing we've been thinking about, but now that we're using the rigid body model, we have to acknowledge that there's this spatial extent. And although, this thing doesn't really change its position, it has, because it's rotating and that rigid body is actually spinning, we have to take into account that rotational kinetic energy when we consider where the energies and what the energies are. But if we do that, we can follow the same sort of reasoning and physics behind it to analyze some situations. We'll do more examples in class and on the homework. Again, as always, if you have questions, reach out to me via email or any other means. And hopefully we'll get comfortable with this stuff.